So I'm very proud of closing the conference. So it is, in fact, a paper in the robotics track, and I'd like to share with you our experience in using MDP and POMDP techniques for real IRL robotics and what we had to do to make them work. So I hope I can play the movies, yes. So the first, one of the first missions we try to solve is an emergency landing mission. So here, in fact, we cannot really see it, but you have an helicopter, an autonomous helicopter, which is approximately twice the size of this table, so it's quite big. From here, you can see the camera on board the helicopter, and the mission here is to automatically land in this environment that we absolutely don't know. So the first thing is to map the environment here with some image processing algorithm. And once the environment is mapped, we extract zones in which we think we can probably land, but it's not sure. So to each zone is associated a probability that indicates how likely we can land in this environment. And beginning from this, then we generate online an MDP whose policy consists in deciding what is the next zone to visit, to explore, and whether in this zone we can land or continue to another zone and so on. So we take into account the fuel level, so the probability of landing in the zone, the distance to the base, and so many things like that. So there are many state variables. And in fact, okay, so you see how it goes. It explores the zone and it will go to another one. So I think you understood how it works. So the problem depends on many parameters that are extracted from image processing at the beginning of the flight, so meaning that the problem must be solved online, okay? And it is, in fact, highly combinatorial because it's, I will see you in a minute, that it is exponential in the number of the zones that are extracted during the flight. But the time is constrained. There is only 15 minutes autonomy available, so we have to take reactive decisions on board the helicopter. So first, at a high altitude, we explore and extract the zone. Then from here, we plan and execute in parallel the policy that dictates which zones to visit. In fact, this benchmark is similar to the search and rescue benchmark in IPPC that we proposed some years ago, and I saw at the conference still people interested in solving it, so it's quite combinatorial. The problem is non-Markovian because you have to memorize basically the history of the zones you have visited, so it's typically exponential in the number of the zone, plus continuous variables. And as I said, you only have 15 minutes to find a zone. So how can we do? So we need for online reactive MDP planning. So just one slide for people who don't know it, but I think on the third day, everyone should know that now. So we have states and actions, observations, if we are in a POMDP setting, probabilistic actions, and in POMDP, probabilistic observations. The aim is to compute a policy that maps states to actions or belief states to actions, which optimizes some criterion, for instance, cumulative rewards. So in the next, I will only speak about states, but whenever the settings will be partially observable, you will replace states by belief states, right? And we all know that for MDPs, the complexity is polynomial in the number of states, but in fact, in real-world missions, we have state features, and the complexity becomes exponential in the number of those features. This is the bottleneck. So why, in fact, in our experience, anytime MDP algorithms are still insufficient? In fact, the clock is running, and you have to take at some time a decision at a given time point. You really need the decision at this time. And you cannot really control the time that is spent in updating states or belief states in POMDPs. So for instance, here in depth of search, you don't really know the time that you will spend exploring this branch, or in breadth first search, you don't know which time will take at least to generate the successors and to compute the heuristic. So you can know the worst case time, the worst case computation time, but still this worst case computation time is not very relevant. in fact, the point is that anytime planning, which consists in quickly providing a first solution and then continuously improving it, is different from time constraints planning, where you have to provide a solution at a given time point. Okay, it's not really the same thing. In anytime planning, in fact, you don't have guarantees that the new current state has been already updated. If it is the case, you don't really know how, so what is the quality associated? And if no action is available, you still have to wait. Or if you have a default action, you can apply it. So one question is, can I tune an anytime algorithm for my specific problem? Imagine I really know the problem, I can exploit the structure of it. And by analyzing state updates, worst case times. So of course you can do that, but in this case, you lose generality, and every time you have a new mission, you use a new algorithm, you have to redo this. You have to do again this analysis, and in robotics, it's really a pain, in fact. We can also use the knowledge of remaining time until the decision has to be taken in anytime planning. In fact, we had an excellent talk, my reader in Toulouse, about this subject. So, of course, it really improves the anytime behavior of the algorithm, but still you cannot guarantee that your action will be available when you need it. And I'd like to mention that this issue was raised, in fact, and studied since the 90s by Thomas Dean, Leslie Kemling, and others in this IAAI paper. But since then, we didn't see much paper about how we can execute and plan in parallel in MDPs. So I'm going to present what we call AMPL. This is, in fact, a replanning framework that allows us to construct partial policies, in fact, ahead of execution. This is the main idea. We don't wait for being in a given state to plan. And we update in future possible execution states while we're executing the current action in our current state. And this will increase our chance that an action will be available in the future. We will replan and execute actions in parallel via a configurable finite state machine whose behavior is known and can be, in fact, model checked if you want to know the time behavior of this framework. And finally, we can drive any existing planner. This is important. Give me any MDP or POMDP planner, right? We can incorporate them in AMPL. It will work like that. Finally, we have to rely on a default policy when an action is not available. So we use planning requests and action requests. So in a planning request, you have an initial state from where you want to construct a plan, the time allocated to the planning task, an algorithm and its parameters. And an action request is simply an optimized action to apply in the current state. All these requests are handled via a finite state machine, whose important part is here. So we can add plan requests, remove plan requests, or get actioned. And here, the states of the finite state machine are important so that the robotic architecture can know what the planning component is doing. And in fact, one control strategy of this finite state machine yields one meta-planar instantiation. So I will show you here two instantiations. The first one is AMPL next, which consists in planning for the immediate successor states. So for instance, in S0, you add a plan request consisting in planning for 10 seconds. It's a bootstrap time. When it's done, then you extract the best action successors. You estimate its execution time, for instance, 6 seconds. And while you are executing this action, you add planning requests for all the successor states. So imagine that you are executing your best action, and now the next state is S2. Then you remove plan requests from those states because there are no garbage. And again, you estimate the execution time and extract the successor states. And you continue to do that. Another strategy consists in extracting the most probable path and balancing the optimization path, the optimization time among the states in this most probable path. So again, here you see the most probable path. And while executing the action in S0, you extract the path, estimate the execution time, and add planning requests on the states. Of course, the most fundamental path can change, and you update the policy accordingly. Okay, so this is a bit technical. It is detailed in the paper, but in fact, we maintain a queue of requests. And this is, in fact, an algorithm, a queuing algorithm that maintains all these planning requests. It is thread safe because we locally copy the policy just on the states of the planning requests. And the most important part is perhaps the solve progress procedure here. So if you take any MDP or POMDP planner, you need to decompose it into small computation chunks that are called by the framework. So I think I must skip this. Yeah, in fact, it was not too short. Yeah, you made it. It's what I thought. Okay. So robotics people like implementation details. So I will give you some details, not too much. So in fact, this sample framework is a planning component, and you can plug any planners. I spoke about POMDP and MDPs, but in fact, we plugged also deterministic planners. So we can imagine that when we plan from successors, instead of using an MDP planner, we can simply start a deterministic planner. It works exactly in the same way without changing anything to the framework. It's simple. In fact, you just have to give some functions. And the most important one, again, is this one, solve progress. So I don't know if I take value iteration, solve progress would just be here a Bellman backup update. And it was implemented in the Orocos framework. And so in this robotic framework, we have multiple components, one responsible for planning, the other for image for vision, another for control laws, etc. And finally, in fact, the planning component is just part of a higher finite state machine that indicates how the mission should be processed, right? So here you have the scanning state, then zoning, and once the zones are extracted, here we launch the planning component, and we execute the policy until the mission is finished. So the planning component here consists in this part. So now some experiments. So we compared the ample next with the ample path strategy, first for random MDPs. So let me explain you how what you see here. So here this is the execution thread. So the time spent to execute the action on board the helicopter. And here in dark gray, you see the optimization thread. So the time spent to optimize from successor states. So yes, and finally, this curve here represents the Bellman error. So when it is 0, it means that, in fact, it has converged. And for next, we see that we spend a lot of time at the beginning to optimize. But then, every time we encounter a new state, we already we optimized ahead of time, so we don't need to optimize again, and we can directly apply the policy. And we see, in fact, that the Bellman error dropped quite quickly. Now for the path strategy. So here, the number indicates the depth of the path. So for path 1 here, in fact, we see that we have to replan again because it was quite short, and the chance of entering a state where no action is available is not 0. You see here that in this state, we have to replan. And when we increase the depth of the path, in fact, the chance of replanning augments. Why? Because as the length of the path augments, in fact, the optimization time that is balanced among the successors decreases for each state. So it means that the chance that the next state has no available action augments. And you see here, with a depth of 3, we have to replan before, and the required effort to plan is higher than here. And with path 5, so with a depth of 5, it's even more. Okay, so I presented an MDP mission. I need to show you how it works with POMDPs also. So this is another real mission. In this case, the helicopter flies over a totally unknown environment, and it has to discover a given car. So for instance, this car. And it does not even know if the car is present or not in the environment. So here, we use an image processing algorithm that analyzes what the camera sees, and then extract the region of interest, and finally tries to match what it observed against the database. It can say that no car is detected, or there are a car detected, but he could not identify it, or he could identify it as a given type, A, B, or something else. So we run this algorithm on many, many images in many different situations in order to learn the probability of observing given objects in the current state. So a state here consists in the position of the UAV, the altitude, the heading, the target's position, identity, and also, I didn't mention it, but the fuel level. Okay, so for instance here, you see the view from the camera of the helicopter. So this is the burst time ISO. And by the way, we use the ample next strategy, so we plan only for the next successor states. So here we are executing the action change the altitude, and while you are doing that, we are already optimizing from the next possible belief states, right? The action is done, we get the observation, then we move to zone 2, and we add new planning requests for the successors. So in zone 2, I see, yeah, there is a car, but in fact, it is a wrong one. So we get the observation, is identified as A, but it's not still sure. The belief state is not perfect, so we will change the view angle. And so it's 10 degrees, so it's difficult to see that it changed, in fact. Now we get another observation, again identified as A, so the belief state is updating. And okay, we accelerate, it changes the angle view sometimes. And I think that it will try another, yeah, so it goes to another zone. Action done, it observes C, and then it's sure that it's a good car, so the mission finishes. So this POMDP, again, is solved online. It is in real time, okay? So the problem was extracted online and solved and executed in less than 2 minutes. So I will finish perhaps with this slide. So we compared AMPL with state-of-the-art POMDP anytime planner, okay, named AEMS. And here, for instance, we gave AEMS 4 seconds to replan if no action is available in the current belief state. Here we gave it 3 seconds, 2 seconds, and so on. In blue, you see the execution thread. In red, the optimization thread. And here we use our framework with the same algorithm. Okay, so we use AEMS in the framework, and you see that, of course, we are optimizing all the time, but we can finish the mission on time, whereas it was not possible with the original anytime planner. And yes, I'm done. Thanks.
All right, any questions? All right, so let me ask you one. So this morning, Malik was saying that acting is actually a deliberative process. And in this case, you're assuming that while you're executing, you basically have free CPU cycles. Now, what if you actually have a constrained CPU where executing takes a lot of your computational power?
Okay, so you mean that executing an action takes so many powers that I cannot compute, in fact, the policy?
Yeah, or maybe do it slower, or yeah, something along those lines.
Yeah, okay. So I would say 2 things. So the first one is that if really you don't have an action, it's always possible. Then you have to apply a default action. Right? So at some point, you must do that. So In fact, we use a default policy that is model checked before the flight. So it is a parametric policy, and we can apply model checking techniques to be sure that it has some properties. And in any case, in case we don't have enough computation power, we use this default policy. And there are some results regarding default policies in the papers too.
Thanks. Yeah. Any more questions? All right, so let's thank the speaker again. And let me also thank